Um, I've had a hard time explaining everything here simply because there were some holes in what I was explaining. I didn't want to write down too much. I hadn't written down enough to have anything to point to, so with apologies, this is a little bit late, but I think we've finally got an explanation of all this. And so I say refer to that explanation as well as to what we have here. And I'm talking about the example of this matrix that reduces down to this. Just briefly, the row space is indicated by the non-zero rows. That forms a basis of the row space. The columns corresponding to leading ones correspond to columns in your original matrix, whatever that matrix might have been, that are a basis for the column space. And we've gone on and talked about what a lot of that means. So we've written down, these vectors, these rows are linearly independent vectors in R5, and they span the same subspace as the original rows of the matrix, and that's what we call the row space. If we have a matrix that reduces down to this, and this is not the A matrix, the reduced matrix of matrix A, then rows 1, 2, 3 are seen to be linearly independent, as we've seen. This row, of course, is linearly dependent on anything, row of zeros. And I made the statement that the original rows 1, 2, and 3 of the original matrix are linearly independent, and that's just not so. Okay, that's the case for the columns. I have no idea why I wrote that, except I think I wasn't having a very good day, and I should have done better than that. Okay. Rows 1, 2, and 3 are linearly independent, and they form a basis for the row space, and I probably shouldn't have crossed that out, but I did. Okay, so another day. Although this is a pretty good day. And this tells us then the columns 1, 3, and 4, this column, and this column, 1, 3, and 4, of the original matrix are basis for the column space. Also say the rank of the matrix is 3. The rank of the matrix is the number of linearly independent rows. You can think of it that way. It has more implications that we'll see later. Okay, now the one thing that's here that isn't in what I've already done is that the idea of the null space. Okay, so this equation AX equals 0 that we've seen, and that's called a homogeneous equation. AX equals 0 is a homogeneous equation because you're saying a product is equal to 0. That's what makes it homogeneous. You got a 0 on this side. That the homogeneous equation also has non-trivial solutions. And the homogeneous equation and its non-trivial solutions of this equation, of this homogeneous equation, form a subspace that we call the null space. Now, I'll simply say the original matrix had 4 rows, only 3 being linearly independent, and it follows in a way that we'll see a little more clearly that the solutions to the homogeneous equation do form a subspace, and the dimension of that subspace is 4 minus 3 equals 1. You have 4 vectors, 4 row vectors, okay? Only 3 linearly independent row vectors, so that the row space has dimension 3, but the vectors that you get out of this equation have dimension, go into a 4-dimensional subspace. And in a way that I'm not going to explain right now, this means that that one dimension you have left over is what you call the null space. Okay, there's a 1-dimensional subspace, which you could think of as a line in 2- or 3-dimensional space. In higher dimensional space, you can still think of it as a line, although you can't visualize it in any simple way. There's a 1-dimensional subspace corresponding to a line through the origin. And that whole line maps onto the zero vector, so that everything along that line collapses down to the zero vector. And that line would be your null space for this transformation. So there's some line in our space, our row space, that collapses down to zero. We'll see how that works out with transformations. You could easily have another row of zeros, indicating, of course, that you're mapping from, you're mapping into R5, and you would have a two-dimensional subspace of your row space. And the null space would be of 2 dimensions. If you have 3 linearly independent vectors and 2 rows of zeros, that really corresponds to your null space having 2 dimensions. So you can think of that as a plane through the origin. More about null space soon. And another thing is we can decompose the solution to any equation, ax equals b, not an ax equals 0, into a null space, a vector in the null space, plus a vector in our row space. We'll talk much more about that.